This video has been supported by Wheelectron. Hey folks, almost exactly 1 year ago I published this first video about my solar power plant plans. Not everything went according to those, which is why this follow-up is coming so late. But it's all done and working perfectly now, so I thought I'd show you a few things. Fundamentally, I just wanted to find a way to lower my electricity bill. Germany had been the world leader in electricity costs for a long time. And now, recent events and my adoption of a lot of electronic test and measurement equipment that wants to be powered on day and night had made it a real concerning problem for me. I chose to buy 11 kilowatt peak worth of used panels, probably from a recent deconstruction of one of these solar farms. A questionable decision for sure, because these do have a limited lifespan. But I checked the labels and datasheets, and these can't be any older than 6 years. So there should still be plenty of life left in them, and I didn't have to pay a crippling amount of money for these 2 pallets. Also, I went into this project with nothing but my inflated ego. I have 0 prior solar power experience. So this is more of a practice piece, and for that I didn't want to use the latest fanciest thin film panels. With this in mind, I'd also like to add a small disclaimer. None of this is professional advice. I'm just documenting my project here for edutainment purposes. There are various flavors of potentially lethal voltages involved. And tangentially there may also be some legal difficulties, so overall this stuff is best left to a professional. Alright, let's jump right into the mortally dangerous and illegal stuff. In the northern hemisphere, a southward facing gable roof is the ideal place to mount solar panels. Because the sun's angle of incidence is the best for most of the time, and the panels get cleaned automatically through rain. South-facing I only have this flat garage roof unfortunately. It does have enough area to lay down all the 50 panels flat. However, a quick back-of-the-envelope calculation indicates that that might yield a lower yearly power output than mounting only half of the panels at an optimal angle. Because of my northern German latitude, the sun's angle of incidence is just very low between autumn and spring. So to generate some meaningful power outside of summer, I need my panels to be propped up at an angle. As I said last time, it's a tricky balancing act to find the perfect arrangement and angle. I want to maximize the number of panels that I can fit on the roof, of course. I want them pretty steep, optimized for the low hanging sun in winter. Because no matter what I do, in summer I will always generate more power than I can consume. They can't be too steep though, or else the row will overshadow the one behind it. In the end, I just let another external constraint dictate the way I mounted these. I've torn down a bit of the decorative wood paneling from my garage roof, revealing that it is mostly empty, except for these huge 100 by 220 mm timbers that are resting on the CNC shed here and on a steel beam on the other side. The simulation tells me that just 3 of these timbers would be sufficient strength-wise to hold my entire solar system and a meter of snow. To satisfy the other requirements, maximum steepness and no mutual overshadowing, however, I'm only going to install half of my panels here. 3 series strings of 8 panels each. This happens to align beautifully on many levels. It's a bit of a sacrilege to puncture a previously watertight flat roof, but I'm confident that I can reseal it with these mounting studs in place. I hope that a minimalist DIY mounting system like this, consisting of stainless all-thread and some 3D printed parts, is going to work for me. Because the alternative would be a commercial flat roof mounting system costing 20 to 50 bucks per panel extra. Alright, time for a quick lunch break. Gas camping stove, steel bucket, and a big old chunk of bitumen or asphalt. It took me a moment to find the correct tool for separating a manageable portion of this 30 kilogram chunk. It seems deceptively solid now, but the slightest hint of heat makes it sticky and goopy. So sawing off a corner would probably only ruin a saw and get it stuck somewhere in the block. A hot wire cutter? No, it would melt back together behind the wire. I could put it into a funnel and wait centuries for a few drops to fall. No, there's got to be a better solution. Aha. Oh, delicious. While the stew is cooking, I'm going to use some large magnets to help mark the center lines of the roofing beams on the roof surface. for finding the strongest points for my mounting studs and not accidentally pierce any electrical wires. The first magnet is simply sticky taped right next to the beam. And with the other one I'm chalking down the approximate location above. The timbers are 100 mm wide, so some tolerance is allowed. This roof is covered in tar paper, and various sources on the internet say that has only a 15 to 20 year lifespan. So it's overdue, and this would be the ideal opportunity to take care of it. But to be honest, I don't really see why. Like, can't I just patch it if it starts leaking somewhere? And anyway, my wallet agrees vigorously. Let's postpone any maintenance until we know how this solar experiment plays out. What? Oh, no, that wasn't one of these absurdly overpowered magnets, playing meteorite and finding a physics-defying trajectory towards a car roof, and leaving a nice crater of impact. No, that didn't happen. I hope this whole construction is somewhat straight. Using stainless threaded rods like this may look a bit amateurish, but it can correct for fairly large height deviations, and due to being a bit bendy, also small horizontal errors. And it's really cheap compared to any alternative. I'm quite happy with it. Big shout out to this drill, which has been with me since before the first CNC machine build. It doesn't have a combustion engine in there, by the way, and should therefore not produce any exhaust.
Pitch needed. More pitch is needed. Not enough pitch, my lord. Pitch stocks are too low, sire.
At the height of summer, where black things outside can reach 40 Celsius and above, this stuff will get quite soft and runny. That makes it kind of self-sealing on one hand, but I'd be worried that it might decide to flow away mostly from this drill hole. So I'm adding an oversized washer to constrain everything a bit more. The remaining stainless hardware gets a quick rinse in acetone, so that there won't be a conflict of interests between Loctite and residual oil from manufacturing. Might be a good idea to do this far away from the asphalt cooker. Apologies to whoever gets to unbuild this in the future, if any. In hindsight, some counter nuts would have been better than exaggerated application of Loctite in these threaded couplers. I used mostly ASA filament to 3D print these UV and weather resistant panel at 13 degree on pole mounting holders. I didn't try to optimize the print parameters for them or anything. They don't have to be pretty. They just have to be present for a few years until I move out and make this somebody else's problem. No, seriously, I genuinely believe that this mounting strategy is going to be plenty strong for any downward forces that the environment can throw at my power plant. It's really mostly just about snow load. Upwards acting forces, i.e. extreme storms trying to send my panels flying, and potentially damaging people or property when they come back down, are a much greater concern to me. But for that to happen, something would have to overpower M10 stainless steel threads, or rip multiple poles out of the timber. I don't think such weather exists yet in northern Germany. Aligning these to absolute perfection is technically not necessary. An angle of incidence of around 90 degrees generates the most power, but it makes virtually no difference if it's 88 or 92 either. A gross misalignment would be visually displeasing, but I guess this unorthodox installation is going to be frowned upon in my normie neighborhood anyway. Stuff like this may only be pleasing towards engineers' eyes. May I direct yours towards the shrubbery shadows on the outermost panels on the left? It almost looks like those shadows counterintuitively encourage early thawing in a mosaic pattern, doesn't it? Yeah, that is the big deal about overshadowing. Each of the 3 rows is a series connection of 8 panels, and each panel is an arrangement of individual solar cells, large area photodiodes that generate electricity when illuminated. However, when insufficiently illuminated or defective, one solar cell will try to oppose the current flow of its entire branch. either succeeding in stopping the whole show or being overpowered, but still dissipating its reverse breakdown voltage times the branch current as waste heat. It's no good either way. We want to harvest every single watt we can get. That's why serious solar panels tend to be subdivided into 2 or more regions, with bypass diodes like these. As their name suggests, these allow currents to bypass an entire segment to avoid congestions. This way, hopefully, a single bird poop won't be able to throttle an entire multi-kilowatt solar string, just a small portion of one panel. So much about the theory. In practice, one of my used panels seems to have a bit of a problem here. It's clean and never under any kind of shadow. Yet this one cell constantly seems to be over 10 degrees hotter than any other one. Is that a rare combination of a faulty cell and a broken bypass diode? Whatever the cause, excessive temperatures over longer times degrade cells irreversibly. So since my plans luckily only involve 48 out of 50 panels, I'm just going to replace this one with another module. Here's the patient, and these are its high-power, low-forward voltage Schottky bypass diodes, for energy efficiency in those hopefully rare cases where bypassing is necessary. They look healthy enough, so I don't know. Anyway, for ease of wiring, strings of similar voltage can be connected in parallel. It only takes a safe DC-rated per string fuse to reduce the risk of a fiery inferno on your roof that could otherwise be caused by a malfunction in one string presenting a load to the very dangerous kilowatt-capable high-voltage sources that are the other strings. Equally important, securing and immobilizing all wiring. We don't want anything swinging in the wind for many years, possibly rubbing against metal parts, wearing through the isolation, ultimately making contact and leaving a deadly 500-volt surprise on a human or bird-touchable metal part. And the final safety feature up here, protective earthing. This is primarily not about protection from a lightning strike. This is about ensuring that all touchable metal parts are at protective earth potential as code demands. There have apparently been cases where harmless low-energy leakage currents have given a worker nothing more than a startling little zap, but then that led to an involuntary movement and a neck-breaking fall from a roof. I'd like to avoid that if possible. I don't have a continuous metal mounting solution here which I could use to ground all the panel frames, so I get to do these point to point, which sucks, but hey, I chose this path. No complaining now. This Bryman AC-DC current clamp from Wheelektron is the #1 time saver in this project. At a glance and without opening any connections, it tells me whether all 3 parallel strings supply roughly the same current to the inverter, or if there are any other dead cells hiding anywhere. It also has no contact voltage detection for finding cables in a wall before drilling, and a peak detect and hold feature for measuring inrush current when powering on a large inverter, for example. It's compact and robust, almost as if someone has designed it specifically for solar installations. But when all that is done, there's also a low current range with a tens of milliampere resolution, making it useful for day-to-day low-power electronics as well. Get yours from Wheelektron, and don't forget about my 5% discount code, which works for other Bryman, most Siglent, and many other products. I have a little bit of footage of how I pulled the PV and a couple of Ethernet cables, for uncertain purposes in the future, through the dead space behind the knee walls. But it's not a pretty sight. I'll spare you the discomfort of watching me struggle in this claustrophobic space. Here is how it's going to look preliminarily after Reps has successfully unstuck himself from that hole in the wall. I think it might be mandatory here for all high-voltage PV cables that enter a building to go through an accessible DC-rated cutoff switch before going anywhere else, just so that the fire brigade can easily disconnect the incoming power in case of an emergency. Then the PV power goes into this one-row electrical panel with fuses of last resort. Normally the 3 per string fuses belong here, but for now I put those and the parallel connection outside on the roof. The orange bits are somewhat futile over-voltage protectors. Generally there is no safety from a direct lightning strike into solar panels, but if there's like a lightning strike nearby, causing a large voltage gradient in the ground, trace amounts will also appear in larger electrical installations. And that's what these guys can offer some protection from. The other devices, especially the big 100 ampere transfer switch in the middle, control where my apartment gets its power from. In one position it connects the public power grid, exactly the way it used to be for the last 30 years. In the other position, which is going to be my default from now on, it connects the solar inverter to the distribution panel on the left. This way, this whole electrical installation is either unchanged from its prior state, or completely grid independent, making it nobody else's business. My hardware is technically incapable of feeding power back into the grid. I'm simply not going to buy any kilowatt hours except for the darkest 2 or 3 months every year. Bottom line, I think this is legal. Only because I've done it myself, I don't expect a fire insurance to pay up if something here ever goes horribly wrong. Alright, now we are ready to soak up a theoretical 3 × 8 × 235 watt over 5 kilowatt of energy that the universe is throwing at us for free. But where to put it? I've tested so many great high-capacity batteries last year, and my inbox is still overflowing with new inquiries coming in every day. There may be other good candidates in there, but sorry, my decision is made. My freshly harvested kilowatt hours are going into these SOK server rack mount batteries. They are durable, safe, easy to connect, and available in local warehouses on almost all continents. They aren't the cheapest per kilowatt hour on the market, but with their internal build quality I feel safe living under the same roof with them. Have a look at my full video about these from last year to find out why I like these so much. Recently the manufacturer has sent over a thick, strong 5-slot rack for them. This bad boy can fit so many kilowatt hours. The batteries are 19-inch wide, but they are too heavy to be supported only by their rack ears. So having something with very strong floors like this is going to be very nice when I ultimately populate this thing all the way to the top. And I get to repurpose this ex-government surplus UPS battery cabinet for other random junk. Thanks to a lot of you guys who've bought their own SOK batteries through my affiliate link, I was already able to afford my second module. I appreciate it a lot. When fully charged, these 2 modules contain about 2 days worth of power for my lab. On one hand, that estimate doesn't include the immensely power-hungry hot water heater. On the other hand, I didn't factor in that even on overcast days my solar panels are still generating a few hundred watt while the sun is out. So only in the 2 or 3 toughest, darkest months, with the shortest days and the lowest sun, do I expect to really empty out those batteries, and to help myself to some good old grid power. I'm connecting the inverter cables diagonally across the parallel battery pack, so that every module gets roughly the same additional series resistance from those short inter-module links. For inter-battery communications, all it takes is a unique ID configured on each dip switch, and a series connection of all batteries through Ethernet cables. With a custom pinned cable, the first battery in an SOK stack can take control over the most popular charge controllers and inverters, such as Victron, Growatt, Solarc, or the various Voltronic flavors, like my MPP Solar branded all-in-one box. That's important because the BMS meters its state of charge very accurately by counting watt hours. Meanwhile, inverters would only make a flawed guess about when to stop charging, for example, based on load and temperature-dependent pack voltage. And that's pretty much it for this installation. Now we just have to wait for the sun to come out and the inverter's turbines to spin up. It really is an immensely loud machine, but 2 doors separated from my workspace. That makes it okay. To tell you the truth, I've actually finished most of this stuff late last year. The neighborhood doesn't seem to dislike my unorthodox installation after all. They even launched some fireworks when I was done. I didn't get a lot of energy out of the illumination, but the gesture is appreciated. Because of my slow-ass video editing, I already have some closing remarks and conclusions to finish this one. I have about a 200-watt standby power consumption in my lab, with a few voltmeters and ADR muse running 24/7. A bit more with computers and power tools running. And a lot more with thoughtless liberal use of my instant electric water heater. That would have given me an approximately €150 per month electricity bill in 2023. Now, even though the first of my 2 SOK server rack batteries was provided by the manufacturer for free, this whole project was still a large investment. $1,000 for half of the used panels, $2,000 for the inverter, $2,000 for the second battery, and probably $500 for mounting, cables and other small parts. If I wanted a complete return of my investment through electricity bill savings, I'm going to have to use this system for at least 3 or 4 years. That would be a great number for a complete new system. But with partially used hardware and a lot of my own labor involved, I would have expected it all to be a bit cheaper. Oh well, factoring in the learning experience, the YouTube video opportunities, and the overall amazing feeling of getting free power from the wall for at least 3/4 of the year, I'm still very, very happy with it. Germany is not an optimal place for solar power. Astronomically, there is an entire season where power production is going to be very low, and you're getting laughable amounts of money and huge bureaucratic troubles for selling power to the grid. Still, there is a lot of political pressure for electrifying everything, cars and residential heating most recently, and paradoxically also for shutting down power plants. It doesn't make much sense to me. Maybe the situation could be improved by implementing variable feed-in tariffs, allowing operators of large batteries to buy cheap power while the sun is shining, and then to sell it for more depending on grid utilization, in the evening or on cloudy days, for example. I don't know, just a thought. When storing solar power in batteries, the first 5 kilowatt-hours gave me the most value. Because with that, every sunny day powers me for the entire following night. The second battery keeps me powered whenever a sunny day is followed by a cloudy one. Everything beyond that is kind of in the realm of diminishing returns. However, I do still want to try and fill that 5-slot rack, because that will lower the per battery current and improve everybody's cycle life. I'm still happy with the MPP Solar 11 kilowatt max inverter. It's been reliable in its first year, except for 2 instances of some kind of software hang-up that needed a power cycle to recover. It is an economy model though, probably sending out lots of EMI into the lab. Most of my DC metrology toys are immune to that, thanks to extreme isolation strategies and long integration times. But if I ever dip my toes into somewhat sensitive RF measurement waters, I fully expect this to come back and stab me in the back. Maybe I have to buy another low-power, low-frequency transformer-based inverter, just to feed the living lab. Not sure yet. What I do know is that I have another whole pallet full of panels, and so much more free real estate on an east-west gable roof. You guys might have to endure another video about this if you're unlucky. But that's all for today. Thank you for watching.